Interacting with the physical world in augmented reality requires both the geometric and semantic understanding of the environment. However, existing AR applications often depend on users to manually annotate such information. In this work, we present an interactive scene understanding system that can automatically model, segment, and annotate physical environments. This enables direct interaction with physical objects in the space. Our system supports spatial search with natural language, and the version control features even keep track of the object changes in 3D. In this video, we demonstrate three application scenarios: automatically parse and virtualize surrounding physical objects, spatial search with natural language queries, and version control 3D environments. We use AR headsets or smartphones to collect RGB and depth information, reconstructing the space from scratch. We integrate deep vision language features and segmentation knowledge into a 3D model of the environment. This allows the device to precisely attach these rich embeddings to physical objects. After just 2 minutes of processing, users can review the reconstruction in various ways: a voxel grid, a mesh model, 3D segmentation, and our favorite form of interaction, directly highlighting and selecting physical objects, like magic. Now that the system knows the precise look and size of physical objects, we can start with something fun by creating their virtual twins. How about a second screen? Or maybe check if the sofa can fit here without having to move the heavy desk. For now, we haven't used any textured material. Have you thought about pressing Ctrl F, but on your room? Our system can perform a spatial search with natural language queries. For example, show me things that might be dangerous to babies. The 3D vision language features generate a heat map that correctly identifies potential hazards: skateboard, the basketball, and the rolling chair. We should never expect the AI model's automatic segmentation or labeling to be perfect. Therefore, we propose human-in-the-loop in-situ learning, a novel machine learning concept that learns from the user's input while they personalize their 3D model. Here's how it works. For example, if the system incorrectly segments one object into two, the user can merge them. While merging two meshes together is trivial, the in-situ learning model will try to automatically merge these similar parts in a future scan of this space. Naturally, user can also rename the automatically assigned labels to be more useful. For instance, it can help clarify the ownership of objects in a shared office space. The in-situ model learns these persistent renaming changes to ensure the same objects are correctly re-identified in the future. These editing features not only correct errors in the 3D model, the merge, rename, and remember actions in fact drive the human-in-the-loop in-situ learning to train a personalized model for the user's space. The real strength of the learned personalized model is that it enables a Git-like difference history to version control 3D environments that help users keep track of the changes in their space over time. When the same space is scanned on a different day, the Unchanged button highlights objects that stayed in the space with their personalized names. But wait, today, some of the objects are missing from the room. Can you count how many objects are missing compared to the previous scan? No worries, with a simple click of a button, we can travel back through time and space to identify all missing items, their shapes, and locations. On the bright side, at least now we know what is missing. To help the development, we also built a desktop software that allows simultaneous access and editing of the 3D model together with a headset. This facilitates collaborative work within the same environment. We often take for granted the significance of being aware of our surroundings and objects in our space, a privilege that visually impaired individuals grapple with. Our system's automatic 3D understanding of space and objects could potentially help them navigate unfamiliar settings with more awareness. Our version control features could alert users about the changes in their space, lending an additional temporal awareness to those with busy lives.